started. So today we're going to look at the other two types of indeterminate forms that we haven't yet approached, and those are what we call the exponential forms. The 0 raised to the 0th power form and the 1 raised to the infinity power form. Now, before you say automatically, oh, but wouldn't this automatically be a number? Well, 0 raised to a positive power is always 0. And a non-zero value raised to the 0 power is always 1. So this is neither one. If I raise 1 to any power, obviously that's 1, but I have a base that's approaching 1. It's not equal to 1. So it turns out that limit here is rarely ever going to be 1. And so we're going to explore these. Now, I would argue the single most important limit that exists that you did in Calc 1, but you accepted without proof. In Calc 1, we do this one here. The limit as x goes to infinity of 1 plus 1 over x to the x power. In Calc 1, we tell you it's e because then that's how we derive a whole bunch of stuff. And if you were in my Calc 1 class, you might remember we did the loan sharking problem, right? Where we compound the interest monthly, daily, hourly, secondly, a million times a second. And, we just have sort of fun with the money problem, and we see that it's approaching the decimal value of e. We can play with our calculators and we can see that. And so the conclusion is, therefore, we know this limit is e. That's because we're told the limit is e. It's not possible for us to calculate this limit in Calc 1. But we're going to be able to calculate it today because we have tools that we didn't have then. So I'm going to go over a problem that we do in Calc 1, and it's one of the more challenging problems. And it's, how do you take a derivative of a function raised to a functional power? And I think we actually explored this one in this class so far. If I was interested in the graph of y equal x to the x power, okay, over off to the side, I know something about this graph, okay? I know a little bit about this graph. I can't take the derivative of this as stated, but we know, okay, for f of x greater than 0, then e to the log f of x is always equal to f of x. That's an absolute, because the e and the log undo each other. And the f has to be positive, because if I'm taking the natural log of something that's negative, that's imaginary. Again, you can't take the log of 0. You can take the log of anything other than 0, but only the log of positive values is going to be real. So this is always true. So the trick to doing this problem right here is we change it to e to the log x to the x. And then, of course, the most important of all of the log properties, you guys know this one, right? Comes down, crashes in front. So we know that, and then that would equal e to the x log x. So now if I want to take the derivative of this thing, I'm just differentiating that quantity, and that's just e to the thing. The derivative of e to the thing, that's fairly simple. My Calc 1 class did that 2 weeks ago. So this one here is not difficult. This is e to the x log x times the derivative of x log x. I'll write it out just so we don't forget what's going on. And that's e to the x log x, and then product rule. First times derivative of second plus second times derivative of first. And so that's e to the x log x times 1 plus log x. And then remembering, e to the x log x came from x to the x. So after all of that, I get this. Great. Now, why is that important? Because this, being the derivative, tells me not only the slopes of the tangent lines, but it also tells me where I have a horizontal tangent. So if I set this equal to 0, this quantity is never equal to 0, but this quantity will. In fact, this equals 0 when x equals 1 over e, or e to the negative 1. So then it'd be 1 plus negative 1. So if x is 1 over e is a little bit bigger than a third. So let's say that's 1 unit and that's 1 unit. So I'm going to go about here. Now, if I put 1 over e into that, okay, so hold on, I'm going to grab my calculator. Okay, so 1 over e. So if I said, take 1 over e and raise it to the 1 over e power, because I'd kind of like to know where that is. So hold on. So, oops, 20 negative 1 raised to my calculator's giving me issues. Hang on a moment. Not sure why. There we go. So if I raise this, I get a value around 0.69. My y value is around 0.69. So it's going to be around there. Okay. Now, what else do I know? Well, this is an exponential function. I know if I put a 1 in there, it's going to be 1. If I put a 2 in there, it's going to be 2. This, in other words, is going to go like this ridiculously fast. 2 to the second, 3 to the third, 4 to the fifth, and so on. Great. So now my question is really what's happening between this point here, which is 1 over e comma 1 over e raised to the 1 over e power. What's happening between here and here? Is this going up like an asymptote? Is it going into the y-axis? Is it going down? Well, we know that this quantity is never going to be 0. In fact, the domain of this is only positive numbers because you can't have 0 to the 0th power. Okay, that's something we know we can't do. So the domain is only positive numbers. So it's either going to go down forever, it's going to go up forever, or it's going to basically have a removable discontinuity at the y-axis. I don't know what it is. I'm not going to play with my calculator and try to figure it out. We are going to take a limit. Now, I suspect it's not going to cross the x-axis because this is never equal to 0. So it's either going to have a finite limit or it's going to have an infinite limit, one or the other. So what we need to do is take the limit. That's our goal. And that's kind of setting us on our path here. We want to take the limit as x approaches 0 of x to the x. Now, we've got to be careful. As x approaches 0, there is no approaching 0 from the left side because the domain's only positive numbers. So we have to approach 0 from the right. That little plus sign is everything. Now, we pretty much know this is either going to be finite or it's going to be infinite, but we suspect there will be a limit. Because if I messed around with my calculator, I'd probably see numbers, although I don't know what they'd be. So now how do we do that one? You can't use L'Hopital's rule. It's not a quotient. So what we're going to do is do the little e to the log trick that we just did to take the derivative and then manipulate that. I'm going to show you what I mean. We already know if we do the e to the log trick, what's going to happen. So this is going to equal the limit as x goes to 0 from the right of e to the log x to the x, which we know will be the limit as x goes to 0 from the right of e to the x log x. Now, this is the beautiful thing about limits. We know the limit of a composition of functions is the composition of the limits. That's like saying, in other words, okay, make sure you're muted, please. The limit of a square root is the square root of the limit. The limit of the sign of something is the sign of the limit. You can always move the limit inside the function. Guys, please mute yourself. Okay, somebody's really loud. We're going to move the limit inside. So the limit of e to the thing is e to the limit of the thing. This is equal to e. This is one of the best parts about limits is I can do stuff like this. Now, e is completely separate from the problem. My entire problem is now this. And as x goes to 0 from the right, the log approaches negative infinity, and this is approaching 0. So this is one of those 0 times infinity forms. Okay, the 0 times infinity form, we know if we make it into a quotient, it would be the appropriate indeterminate form. So do I want to throw the log downstairs or the x downstairs? It's the x. We saw that last time. It makes it a little bit easier. So this is now equal to e raised to the limit as x goes to 0 from the right of the log x over 1 over x. And again, the entire problem we're looking at, the limit is only this. this is now the appropriate type of indeterminate form. My numerator is going infinite, it's negative infinity, but it is still going to infinity. The denominator is going to infinity. This is an infinity over infinity form. I can now use L'Hopital's rule on that. Okay, bring it up. And here's the beauty of this. I can say this is equal by L'Hopital's rule because we're applying L'Hopital's rule to the limit, not to the e. I can't do L'Hopital's rule with an e there. I can only do L'Hopital's rule on a quotient. So this would be of e to the limit as x goes to 0 from the right of what? The derivative of log would be 1 over x. The derivative of 1 over x would be negative 1 over x squared. And that quantity can definitely be reduced. And this 1 over x over negative 1 over x squared is just negative x. I can now evaluate my limit. As x goes to 0 from the right, this is approaching 0. So my limit is e to the 0, which is 1. Oh, so as x approaches 0 from the right, my y value is approaching 1. And that means I have a removable discontinuity at that point, which is very cool. We couldn't do that in Calc 1 because we didn't know how to do the limit in Calc 1. Now, exponential limits are the hardest type of limits to take because you have to change the problem. You have to convert it to something else. You have to convert it into something that you can use L'Hopital's rule on. L'Hopital's rule primarily was created, basically, its use for this type of problem, because we already know that if it's trig in nature or if it's algebraic in nature, you never have to use L'Hopital's rule. And in fact, there's a lot of algebraic problems we found that using L'Hopital's rule actually was a dead end, right? You got into an infinite loop. Although it's legal to use L'Hopital's rule, sometimes it's not always efficient. So although I can use it on any indeterminate form of the 0 over 0 or infinity over infinity variety, if it's algebraic in nature, there's actually ways you can do without. In fact, in general, I can show you how to do limits without ever using L'Hopital's rule and still be faster at the limit when it's legal. The exception is if there's a log involved. If there's a log involved, L'Hopital's rule is the only way a limit can be taken. There's no algebraic trick to manipulate something with a log in it. That one has to be L'Hopital's rule. So this is the only way to get there, but it's kind of cool. So now let's look at the problem that we've seen really since intermediate algebra, and that's this one. We have the limit as x goes to infinity of 1 plus 1 over x raised to the x power. We want to look at this guy right here because we know what we're supposed to get. The question is, how the heck do we get it? We're told the result, but we should be able to find the result. So the first thing we're going to do, I'm going to do this as a separate step. We want to rewrite the argument here. 1 plus 1 over x raised to the x is e to the log 1 plus 1 over x raised to the x. Okay, I know that's true because this quantity here is strictly positive. And then, of course, this guy here, love the sound that it makes. Then that is e to the log x, or excuse me, e to the x, sorry, e to the x log 1 plus 1 over x. So this is equal to the limit as x goes to infinity of this quantity right here, e to the x log 1 plus 1 over x. Now there's two steps I have to do. I have to get the e outside the limit. And then secondly, I need to examine the type of indeterminate form that's going to produce. This is not an indeterminate form. E to something is not an indeterminate form. The exponent is eventually going to be an indeterminate form. So this is e raised to the and x log 1 plus 1 over x. Now, as x grows without bound, obviously x is approaching infinity. But what's happening to this part here? What is the form that this is approaching? As x grows without bound, 1 over x we know is approaching 0. So 1 plus 1 over x is approaching 1. Therefore, the log of 1 plus 1 over x, we know log of 1 is 0. That quantity is approaching 0. Okay, so again, as x grows without bound, that whole thing right there is approaching 0. So this is the right kind of indeterminate form for me to start with. So I got to move one of them downstairs. Clearly, it's going to be the x. Now, I do want to caution you when you're writing this. Don't do this. I have a lot of people that will end up doing this. That e being raised to the limit at some point becomes e multiplied by the limit. That would be quite a big error. Okay, that would change everything. I just made e, I went from b being the base to e being a coefficient. No, I won't get the same answer. So make sure your e is staying in the base position. So this would be the limit of, now, the log 1 plus 1 over x over 1 over x. Now here's the thing. I'm going to pretend I have no idea what the answer to this is, but I do know whatever this equals, it does equal this, and whatever this equals, it does equal this. I know I have a series of equal signs. How do I know? Remember, the ultimate proof with a limit is if you cover up the word limit, then are the quantities algebraically equivalent? So if I covered up the word limit, yes, this quantity is equal to e to the log of that quantity, and so on. All of the quantities are equal if I cover up the word limit, so now I can evaluate. As x grows without bound, this is approaching log of 1, which is 0, and the denominator is also approaching 0. So this is a 0 over 0 form this time. I can use L'Hopital's rule on this, and I will get, oops, sorry, I'll get e to the limit. Actually, let me write it down. Now, I'll squeeze it in here. Okay. The derivative of the log of thing. Okay, it's 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. The derivative of 1 plus 1 over x is negative 1 over x squared. The derivative of 1 over x is also negative 1 over x squared. Actually, I don't really need the parentheses. And clearly, I can do that. Got lucky on this one. So now we've got e to the limit as x goes to infinity of just that. Now, as x grows without bound, 1 over x is a transient term. So I know that's going to 0, which means this quantity is approaching 1. So my answer is simply e to the 1. And that's the proof that that limit is e. I never used any properties that it was e. That was our result. Cool. This is considered the most important of all the limits, and this is how we get there. Kind of nice. Now, I've just done two different examples. The first one was a 0 to the 0 form, and this one was a 1 to the infinity form, but I attacked them both the same way by using the e to the log trick. Now, there's something I want to show you from a notation standpoint that you're going to run into, and it might confuse. If you are a programmer, anybody here who's ever written any code, you know you can't write e raised to the x power. There's no way of writing that if you're writing code. So how do you write e to the x in code? Well, in computer code, e to the x, we generally write it as exp of x. Some of you may be familiar with this. This is kind of the computer code for this, because I have to be able to write it as one line, right? I can't enter an exponent when I'm writing code. So what we often do in a problem like this, we often use exp, not because it's superior. Oh, no, not even close. But look at what I have here. I have e raised to something. Within the something, there's a quotient. Within my quotient, I have other quotients. On my computer, I use generally a 12-point font. Superscripts, which was what exponents are generally then a 7-point font. Within the 7-point font, numerator and denominator are usually going to be 3 or 4-point fonts. My point is, every one of these symbols is going to get smaller and smaller and smaller and smaller on the computer screen and become very difficult to read. So one of the reasons that people will often use the exp is then this comes out full-sized. You see, it doesn't come out as an exponent. You see, already this is only 7 points, and that's now squished. So I will use that often when I'm writing a key. I will use the exp notation so that I can keep all this stuff really big. When I'm doing this by hand, no, I don't need to. You can clearly see this, but be mindful, right? This is kind of universal notation, but not everybody uses it. Some textbooks will. Other textbooks will just keep making their stuff smaller, hoping you can read it. I find that one to be kind of difficult sometimes. So if I had typed this is a good example. If I typed this on the computer, all of these symbols would have been really small and harder to read. So I would have put EXP of all of this stuff. All right, so let's try another one. See something a little more complicated. Suppose we want to find the limit as x goes to infinity of, how about 1 minus 3 over x to the 4x power? You throw some different numbers in there at you. Okay. Well, we're going to attack this just like we did the previous one. And if you'd like, you could do the following. I don't write, when I'm doing an integral and I have to do algebra, I don't like writing the integral equals the integral equals the integral equals the integral while I'm doing all of my algebra. I usually like doing all the algebra as a separate step so I can write the integral equals, the thing that's ready to evaluate. Well, I have to do a whole bunch of steps before I can do anything L'Hopital-ish on this one. So why not start the problem by doing something like this? Now, I know I got to put the x downstairs. I don't need to move the 4. Leave the 4 there. If you put the 4 downstairs, it just makes it a little more confusing. You're not sure what to do with it with a derivative. I need to move the x downstairs. So this is equal to e to the 4 times the log of 1 minus 3 over x, all over 1 over x. Algebraically, this quantity here and this quantity here are identically equal. They're exactly the same thing. But I just did all my scratch work ahead of time. So I can now say, and this is equal to the limit of this thing. Now I'm almost ready to do L'Hopital's rule, except the e is still inside the limit. I cannot evaluate it yet because it's not an indeterminate form. This part's an indeterminate form, but the e is in the way. So the next thing, which is the easiest thing of all, is put the e on the outside and make it really clear that this is an exponent. So I have 4 log okay. Now, all the calculus is going to be done on that. The e is completely external to the problem. That's one of the beautiful things about limits, is that I can move it in all the way inside the problem if I choose. I moved it far enough inside that I now have an indeterminate form. As x grows without bound, again, that quantity is approaching 1, so log of 1 that's approaching 0. My denominator is approaching 0. This is the right type of indeterminate form. I can now apply L'Hopital's rule to that. All of this algebra was to get it to the point where I could actually do L'Hopital's rule on the problem. Okay.
So, Mr. Brown, would you accept if we're writing this up for a quiz or a test to combine the last 2 steps into one?
You're saying just go from here to here?
Yeah.
Yeah, as long as you're not getting lost in the process. Yeah, that's okay. Because really what we did was we said the limit of this thing is equal to the limit of this thing, because what I was doing the algebra on the thing. The moving the e to the outside is really a completely different step, but could you? Yeah, most people really do at some point. You don't want me doing that though, because then I lose everybody. So
thanks.
I do from here to here clearly required a few steps, but I like doing those steps kind of like off to the side. So I'm never going to go from here to here without justifying it, because I might make a mistake for one. Also, people will say, how the heck did you get from there to there? Well, I did the algebra. So, okay, then the limit of the thing equals the limit of the thing because the things are equal. And now I move this. By the way, I could stop right now and everything I've said is the truth. I just can't evaluate this yet. That's why we do this. But the question was, can we go from here to here? Yeah, as long as you're justifying where everything came from, that's okay. you don't want to skip steps though, because then the problem is a lot of times this won't be a correct quantity because we try to do too many things in our head. And if you do it in your head, you're never going to find the error. So this is now e to the limit of, just like before, it's 4 times, okay, 1 over 1 minus 3 over x. The derivative of the derivative of 1 minus 3 over x. Well, let's see. If you can't do that in your head, then do it off to the side. Okay. That's minus 3x to the negative 1. So the derivative would be 3x to the negative 2. If you have to do it off to the side, then do it off to the side. So that'd be times 3 over x squared. And what's really important is this is positive. That's actually huge. The derivative of the bottom I know is negative 1 over x squared. There's nothing wrong with leaving it as a negative exponent, because the most important thing you notice now is that those guys will cancel. But that sign is huge. If I get the sign incorrect, it will change my final answer significantly. So now I've got equals, because I'm just simplifying the algebra. I'm only going to do L'Hopital's rule once in this problem. My numerator is 4 times this quantity times 3, but I have a negative 1 in the denominator. So that's actually negative 12, if you will. I'm going to write it like that. Now, I can multiply top and bottom by x, and I can do other stuff, but I can evaluate this limit right now. I don't need to manipulate this part here algebraically, because that's a transient term. It's going to 0. So right now, this is approaching negative 12 over 1. So my answer is e to the negative 12, or 1 over e to the 12th. If I mess up that negative sign, my answer would have been e to the positive 12th, which is a little bit different. One is infinitesimally small. The other one was astronomically large. So I don't want to mess up that negative sign. That would really, really mess me up. But it's kind of cool. Doing a problem of this nature is really not that hard algebraically. And I only take one derivative in the entire problem. Okay, I'm going to take the derivative of the log of something fairly simple. Let's do one more example. Now we'll go back to the other kind. All right, let's do something somewhat diabolical, shall we? How about we do the limit as x approaches 0 from the right of, how about how about trying to think of something really nasty. How about x raised to the sine x power? Oh, that just looks horrible. I have no idea what the answer is. That makes it more fun. Now, is it possible that the answer could be infinite? Yes, it is. Is it possible that it's finite? There's a very good chance that it's finite. Is it possible it's a D and E? Well, it's less likely to be a D and E because I'm approaching it one-sided. Had I asked to approach 0, period, now we have a problem because the base has to be strictly positive. So this one can only be done as a one-sided limit. So off to the side. I have sine x log x. That's just awful looking. That is just truly, truly terrible. Now, will we reach a dead end on this one? I don't know. I think there's a very good chance we could end up reaching a dead end on this one, because this is approaching 0 and this is going to be approaching negative infinity. And which one do I move downstairs? Ooh, that's the hard part. The one that I move downstairs, because I can't really do 1 over log very well. And that would become a cosecant. So this is going to be interesting. So let's see what happens in this case here. And then last, I'm going to write this then. Make sure I didn't lose anything. I'm going to write this as cosecant. Now, we hate cosecant because cosecants never go away. But my cosecant's in the denominator. which means after I L'Hopital it, I might be able to move the results back to the numerator. And so in other words, I might have a way out of this. So this is going to equal the limit as x goes to 0 from the right of this, of e to the log x over cosecant x. Now, just to be sure, since the sine function goes to 0 positively as x goes to 0 from the right, the cosecant function is going to approach positive infinity. We know it has a vertical asymptote. So this is basically of the infinity over infinity nature. So e to the limit, excuse me, x goes to 0 from the right of log x cosecant x. Now let's see what we get. We're going to L'Hopital it. And we're going to get e to the limit as x goes to 0 from the right of 1 over x over negative cosecant x cotan x. And that's a big yikes. But I can move these guys back into the numerator easily enough. The reciprocal of the cosecant, of course, is the sine, and the reciprocal of cotangent is the tan function. So now I have negative sine x tan x over x. As x goes to 0, that's going to 0, that's going to 0, and that's going to 0. This is actually perfect. Why? Because if I apply L'Hopital's rule again, my denominator is going to be a 1. And my numerator is going to be all happy stuff. So it turns out this was the right route to go. So we're going to go L'Hopital again. That's why we love it with the x's on the bottom. So a little product rule here. So negative sine times the secant squared plus the tangent times the, negative cosine. I don't know how to get that in there. Okay. Now, as x approaches 0, secant's approaching 1, sine's approaching 0. So that term's approaching 0. Cosine's approaching 1, well, in this case, negative 1, but the tangent's approaching 0. So that means this limit is, I'm sorry, I lost my e there. Sorry. This limit is 0. So my answer is e to the 0. How interesting. Okay. Now, before we move on, because we're going to go to something very, very, very different, are there any questions? No, it's too soon.
Would it be permissible, instead of doing L'Hopital's rule for a second time, to say that the limit, you have the limit as x goes to 0 from the positive side is negative sine x tan x over x, and the sine x over x part can go to 1.
I love it. Yeah, now you're using a prior fact. Yeah, everybody, let me switch colors. He's saying we could also think of this as sine x over x. Remember, the limit of a product is the product of the limits of, I believe this is what you're saying. Is that correct?
Yeah, right.
And we know as an absolute fact that limit is 1. We prove that one in Calc 1, and then we can easily calculate that one to be 0. Yeah, I love that idea. That's being clever, because you're saying, wait a minute, I know a result that I can manipulate. Kind of like if you ever get the e, the 1 plus 1 over x raised to the x power. If you ever get that statement in something, you can do that. So, and by the way, I'm glad you pointed that out, because would you say these are vastly different routes? Doing L'Hopital's rule a second time? I think they're vastly different routes, but we're going to get the same answer. That's a good thing. If you can do the same problem correctly from 2 different points of view and get 2 different answers, that's a bad thing. So we took 2 very different routes to get the answer. We got the same answer, because this is 1 times 0. So my answer is e to the 0, or this was e to the 0, and I still got the same thing. So this, yeah, if you see this, that's awesome. That's awesome. So how do you know when you're going to do this? Well, it's the form. you have an exponential type of situation where your base and your exponent are both approaching 0, or your base is approaching 1, your exponent's approaching infinity. That one will look a lot like the E, the definition of E. That one looks much more like that one. The 0 to the 0 power often is going to function to a function power form. And both of those are not automatic. They require some work. So this is the primary reason you learn L'Hopital's rule, is for these types of problems, because there is no other way. If there was an algebraic approach, trust me, I'd show you. Now, there are other ways to do limits that we're going to learn in the upcoming weeks that have nothing to do with doing calculus stuff. It's a totally different way of doing limits. And it's kind of cool. It's not necessarily faster or efficient. All right, so we're about to do a particular type of integration that is going to be really weird at first, but it turns out it's a very powerful tool to doing some of the things we're going to be doing over the next few weeks. And here's what I want you to think about. Okay, I'm going to do a simple problem. I want to integrate y equal 1 over x squared. Okay, piece of cake. And I want to go from 1, how about to, I don't know, infinity. I think that might be kind of tricky. Infinity is not a constant. You cannot ever take a function of infinity. That has no meaning mathematically. Infinity can only be reached or used as a limit. So I can take the limit of something and have infinity as a result. I can take the limit as x goes to infinity and then look at the behavior. That's what we just did. But I can't say, okay, what's the cosine of infinity? You know, what's 3 times infinity minus 2? No, infinity is not a constant. It cannot appear in an algebraic manipulation at all, ever. Although I find that Calc 2 students are really good about manipulating infinities and adding and subtracting them, and infinity minus infinity is 0, infinity over infinity is 1, you know, infinity times 0 is 0. No, infinity is not a constant. You can never use it in a statement like that. I have an infinite limit. Okay, that's a problem. This is what is called an improper integral. It's the kind of integral you don't bring home to your parents for dinner. It's, you know, totally inappropriate. No, it's improper, not inappropriate. An improper integral. So I want to think of this problem in a different way. Let's consider a graph, shall we? Now, the graph of y equal 1 over x squared looks like this, but I'm going from 1 to infinity. So looks something like this, and that would be 1. And I'm asking you, technically, what is the area below the curve? So I'm actually asking you to calculate that area. Now, it is true that that goes forever, but that makes this problem actually not that terrible. That means I only have 2 possible choices for my answer. My answer is either going to be an infinite amount of area or it's not. And if it's not infinite, that would mean it's finite. But it's definitely not going to be a D&E because nothing weird is happening. I don't have discontinuities. I'm not dividing by 0. No, it's either going to be infinite or it's going to be finite. So how the heck am I supposed to figure that out? Then I'm going to change the question. Let me take an arbitrary value, call it t. T being greater than 1. Just pick any number bigger than 1 along the way. And I want you to find that area right there. Okay? So let's change the problem. Let's change the problem into the integral from 1 to t of 1 over x squared dx. I think this will be easy to find. Okay, so the antiderivative, if you want to write it as x to the -2, the antiderivative would be -1 over x from 1 to t, which would be -1 over t plus 1. Great. That's it. The answer to this question for any value of t that is greater than 1, the answer, that area is going to be this. Now, I'm going to let t get bigger and bigger and bigger. In fact, I'm going to let t go in a general that way direction. How about, I don't know, forever? Can I put an equal sign between these two things? I left a space here, by the way. Can I put an equal sign between these? Do you see anything? Not yet. But if t gets bigger and 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 bigger, then
You're at a limit as x goes to infinity.
not x,
Or as t, yeah.
t goes to infinity. Now, does that make sense to you if I write it like that? Okay, so t is a finite number and it gave me a finite result. Now, if I allow t to approach infinity, I would be back to this statement here. But I'm not calculating infinity, I'm calculating it at t. So the answer to this question would therefore be the limit as t goes to infinity of -1 over t plus 1. And what is that answer? That would be 1. Whoa. This is an improper integration, but you're going to find when you have an infinite limit, generally speaking, it's not going to be very hard. If you can integrate, if you can work with the integrand as is, then taking the limit, and this sounds kind of weird, you're going to take the limit of your limit of integration. That can be a little bit tricky, but the new problem is probably not that bad. So here's what happens. All right, you figured it out. Now, we're going to go into the painting business, a couple of us here. You know, me and Joshua, we decide we're going to make some money on the weekends, and we're going to start a painting business because down in La Jolla, those people have a lot of property, and some of them actually have infinite fences. They have fences that go on forever, but they decrease. And so we're going to market ourselves to this new area with the people with infinite fences, and we're going to call ourselves, of course, the Infinite Painters. That's going to be the name of our business. I've already trademarked it and all that stuff. So we're going to market ourselves to all the people that have infinite fences, and we'll bid the jobs, and then we will paint their infinite fences. Because you see, this is only an area of 1. Maybe that means I only need 1 gallon of paint because it's getting so small. I can just tilt the fence and let the paint run downhill forever. A lot of reasons. So our very first job, somebody comes to us and says, yeah, okay, I heard you guys do good work, and I'd like you to paint my 1 over x fence. And we're like, piece of cake, we got this in the bag. And so just to be sure, we decide, maybe we should graph, what does their fence look like? Well, the graph of y equal 1 over x doesn't look a whole lot different from 1 over x squared because the x is greater than 0, right? There's something down here, but that's irrelevant. And just like before, okay, it's almost the same problem identically. So we bid the job. They're going to pay us a lot of money to do this job, and so we're going to start setting up the process. And of course, we pretend like it's a lot of work. And as soon as they leave, we quickly do our integrations because we're good at this stuff now. So this we'd say is the limit as t goes to infinity of 1 to t of 1 over x dx. Now you're not taking the limit of the x. X is the variable. You're taking the limit of the constant. If I take a limit for x, it's going to change everything. So the antiderivative of that I know is what? Natural log absolute value of x, and I'm going from 1 to t. Okay, piece of cake. So far, so good. Easy money. All those people with infinite fences, they're going to be, just giving us their life savings, maybe. Well, these are both positive values, so I can drop the absolute value. And of course, I know this guy here, that's 0. So my answer is simply the limit as t goes to infinity of log t. And as t goes to infinity, what's happening to log t? Anybody? What's happening to log t as t goes to infinity?
Also going to infinity.
Also going to infinity. Oops. We bid this job, and turns out it's not a finite area of fence. It's an infinite area of fence, of which would require an infinite amount of paint. And so, of course, we quickly reorganize, declare Chapter 11, do all the legal, stuff, and change our name, of course, to the infinite in certain situations painters or something. We did a problem that looked almost exactly like this one. We did it with an x squared. We got a finite value. I changed it to this. We got an infinite value. It wasn't an automatic no-brainer. I actually had to do the problem and saying, okay, that's not. I can't just automatically assume it's finite. So here's what I'd like to know. Is there a line in the sand? And here's what I mean by that line in the sand. Here's the problem we want to address, because this is the result we really want. One over x to the p. Now, we've just done 2 problems. We did a problem where P was 2. We did a problem where P was 1. P equal 2, it converged. I'll go over what that means. And P equal 1, it diverged. I'll go over what those words mean in a moment, because these are going to be the new most important vocabulary words you're going to learn. I'd like to know, for what P does this, is it finite, and for what P is it infinite? Now, if P is a negative number, or if P were 0, understand if P was a negative number, then I actually have the X on top, and that means it would be growing without bound. You know, if I said this is a parabola or a cubic from 1 to infinity, obviously that's infinite because it's growing without bound. So no, we need the one that's shrinking. So I need P to be a positive number to begin with, right? P is not going to be a negative number. Now it could be, but it would be kind of silly to say, oh, I'm going to do 1 over P to the -10th. That means this is going to infinity very, very quickly. So I need to integrate this one. Now, remember, we already did the result for P equal 2 and P equal 1. And I know the result for P equal 1 already. So let's say that this P is not equal to 1, because I want to be able to integrate this for any value of P except 1. Because remember, 1 over X has a different antiderivative than 1 over X to a power. So if I rewrite this now as the limit as T goes to infinity, I'm partial to T in this case, of 1 to T, how about I rewrite that as X to the -P? Might make it easier to see, okay? So that will be the limit as T goes to infinity of, now, add 1 to the exponent, and then 1 over that value, okay, from 1 to T. So I can pull that out in front if you'd like. I can write that as 1 over 1 minus P. And then on the, what I have left is the limit as T goes to infinity of what? Of T to the 1 minus P power minus 1 to the 1 minus P power. Ooh, so T is going to infinity. Does that mean that's going to infinity? Or does that mean that's going to 0? Could it be either one? It kind of depends on P, doesn't it? Does everybody see that right now? Kind of depends on whether that's positive or negative. So if that's a positive quantity, if 1 minus P, let's write it this way. If 1 minus P is greater than 0, what the limit is infinite. Okay? Because 1 over 1 minus P, that's just a coefficient, that's a constant. If this is a positive number, then I have the base growing without bound raised to a positive power. Clearly, that's infinite. But what if 1 minus P is negative? If 1 minus P is negative, then doesn't that mean that technically the T is now in the denominator? And if the T is in the denominator, it became a transient term, and therefore that term would approach 0. And my answer would simply be this times -1, which I could write as 1 over P minus 1. So it has everything to do with the sign. Now let's check this out. If 1 minus P is greater than 0, the limit is infinity. If 1 minus P is less than 0, then the limit is a constant. Okay. Now, when we did it a little while ago, we used a P value of 2. And our answer was, in fact, 1. That's 1 over 2 minus 1, by the way. Then we did an example where we used an exactly 1 and it was infinite. Okay, so 1 minus P being greater than 0 is the same as saying what? P is less than 1. So guess what? We are going to go ahead and give a conclusion. We'll reach this. I only have 2 possibilities. What does it say? P is greater than 1. If P is greater than 1, that means that 1 minus P is less than 0. I'm going to get a finite limit. We just did it. But we just did it for P equal 1 a moment ago, and that was our log case. So I'm going to put or equal. This guy here is infinite whenever p is less than or equal to 1. And by the way, that would then encompass if p was a negative number, because then it just meant the x was on top. And if p is greater than 1, x squared, x cubed, x fourth, whatever, then it's going to be finite. Turns out this result is really, really important for the next few things we're going to do. Okay, now I used some words that I'm going to now use this. We're now going to change the way we say things just a little bit, because we're going to expand our vocabulary. Okay, I've got the limit as x, and by the way, whether I'm approaching infinity, whether I'm approaching a constant, it does not actually matter. So I'm just going to say the limit as x approaches a of f of x, and I'm going to allow a to be infinity, a for anything that I'm approaching. You actually have three possibilities for a limit. We know this, right? If you don't remember anything else from Calc 1 on day one, a limit is either finite, infinite, or it does not exist. Those are the only three possibilities for a limit. Undefined isn't a possible answer for a limit, because that means we're trying to divide by 0, and 0 is not in the domain. Yeah, that one's right out. So if a limit is finite, infinite, or doesn't exist, then we say it like this. This is finite. We say the limit converges to whatever that number is. So if I said this limit is 10, then we'd say our limit converges to 10. The word converges means I had a finite limit. If the limit was infinity, we say the limit diverges to infinity. Diverge is a completely different word and a completely different meaning. Now, in English, diverge, that's a confusing word, okay? Because the root die, what does die mean, right? Di. Right now, every word in the English language that starts di means you have a dilemma.
Two.
The voice means two. Dihydrogen oxide, it's water. Yeah. Di means two. Oh, carbon dioxide, right? CO2. Yeah, di means two. Bi means two. Para means two, but it's a context. And one of the things that confuses people in mathematics, we use bi a lot more than we use di, because when bi is used, like bisect, it often gives the implication that it's like an equal split. That's kind of one way of thinking about it. So I always like using the example of divorce. The word divorce means a separation or a split of two things. Like you divorce yourself from your work, you divorce yourself from your company, you divorce yourself from your spouse. There's a split, but it's not necessarily an equal split. It's just a split into two. Okay, di means, in the English, di always means two, but it's confusing because it doesn't mean it quite the same way, right? Two roads diverged into a wood, and I took the one less traveled by, and that has made all the difference. Okay. Famous poem. That divergement, the roads split into two directions that were never going to come back and converge into one. So the concept of converge is that you are approaching one thing. Diverge is that you're really not approaching one thing. Rather than think of diverge as being that I'm approaching two very specific things, it's I'm just not approaching one thing. So in this case, diverge means I'm not converging. Because the third case, DNE, means to diverge without limit. There is no value I can give you, but it is most definitely not infinity. We like this kind of divergence. A parabola diverges to infinity. I can see its behavior. I can see where it's going. But things that oscillate and bounce around and don't approach any particular value, we don't like those. They're harder to work with. This is the worst. When the limit doesn't exist, it means something diverged without limit. It doesn't mean it's growing infinitely large. It just means it's all over the map. It's not approaching any specific value. So from now on, we're going to start using these words. And it turns out in the long run, we will be less concerned over time as to the nature of the divergence. Basically, as we go on and on, things converge or they don't. If they don't converge, they diverge to infinity, or they diverge without limit. But we will be less concerned down the road as to the nature of the divergence, just that it didn't converge. Because we're only interested as we go on in answers that converge, because those are going to be the only ones that are actually useful to us in real life to answer questions. Okay, so we say that this integral converges to this value when p is greater than 1. That's the correct way of saying it. This integral diverges to infinity when p is less than or equal to 1. Okay, that's how it works. So let's do another example of something of this nature that might be just a little bit trickier. All right, let's do a what if. So now I got the limit, and let's say I want to make this one a little bit more diabolical, shall we? So maybe we've got, how about the square root of 3x squared minus 6x plus 5. And on top, I have 4x minus 4. And I'm going to go from, how about, let's see. Let's go from maybe 2 to 4. I'm sorry, not 2 to 4. I'm sorry. 2 to infinity. What am I saying? 2 to 4. Ha. All right. You look at this going, I have no idea what to do with this one. In fact, let me make it even worse. Let's make that third power. Yeah. I'm in a particularly diabolical mood. Is this basically the last problems we just did? Yeah. Because I'm going to infinity. But it's not just 1 over x or 1 over x to a power. So very first thing I'm going to write is that this equals the limit as t goes to infinity, 2 to t. Now, it might be easier if I rewrote this maybe in this form. 3x squared minus 6x plus 5 to what power, though? Anybody?
-3 halves.
The -3 halves. That one always kind of get in trouble sometimes, and times 4x minus 4 dx. Now, here's what I would suggest. A U-substitution probably makes perfect sense, but when you do a U-substitution on a definite integral, there's two things going on. If you don't change the limits, then anything you write after that's completely irrelevant, meaningless, because it's a completely unrelated problem. And in a definite integral, under no conditions do you ever change back. There is no such thing as a substitution back to the original variable in a definite integral because it's a numerical answer. I'm not sure I want to keep track of all the limit changes. I think that might make it just a little bit too difficult. So here's what I'd suggest. Do the indefinite integral. I think this is safer. And you know you can do this. In Calc 1, you know it's legal to do the indefinite integral and then come back to the problem. And it might be safer because the nature of this problem, I'm already changing my limit of integration and I'm taking the limit of my limit. And now I'm going to do a change of variable and change this guy and take, you all see where that can be a slippery slope, as they say. So think of this really as a separate problem. I think it's safer if I do this. Let u equal 3x squared minus 6x plus 5. Then my du is 6x minus 6 dx. How about if I rewrite that as 6 times x minus 1 dx? And how about if I rewrite that as 4 times x minus 1? Okay. I have exactly what I need. I just have the wrong multiplier. Okay. So the easiest way to do this, I need that to be a 6, don't I? So in case you forgot what you can and can't do, you can always manipulate constant multiples. So here's what I would suggest. Put it here. Now, I need it to be a 6. So I'm going to introduce a 6 over 6. Quick check. 4 over 6 times 6 is in fact 4. So I have not changed the meaning. But now I can integrate this smoothly. It is now of the form 4/6 or 2/3, if you will, u to the -3 halves du. Okay, remember you have to have exactly the chain rule factor, not something similar. The antiderivative of this, well, that'll be u to the what? U to the -1/2 times -2, so times -4/3. Okay, and then finally, didn't leave myself a lot of room, -4/3 times my original u, 3x squared minus 6x plus 5. and it would be to the 1/2 power. It would be totally appropriate to write that as a square root if you chose. Now, here's why we did this. I have absolute certainty that the antiderivative of my original integrand, not the with the limits, but the original integrand has this as an antiderivative. Therefore,
Wait, isn't it supposed to be negative 1/2?
did I lose a? Oh, thank you. Negative 1/2. Sorry.
Yeah, sure.
Thank you. Yeah, I think that one will matter. Now, I said it's totally appropriate to write that as a square root. In fact, it might even be easier to interpret if you write it as a square root. But in the bottom, so I'm going to now write. I'm showing you the nastiest kind of problem, and this is the easiest way to navigate. Do the calculus off to the side and now come back and answer the question. So I'm going to write the antiderivative, which is -4/3 times the square root of, if you want to write like this, minus 6x plus 5 from 2 to t. Okay, let me stop for a moment because I need to erase a little bit of this now that we have that. Now, you can't take the limit yet because there's no t in here. A lot of folks want to take the limit right now. There's no t's. I have to evaluate it, put t's in, then I have something to take the limit of. If I take the limit right now, I'm just making this be infinity and I still haven't addressed this. So the next thing I'm going to do is evaluate this bad boy. So this will be -4/3 times the square root of 3t squared minus 6t plus 5 minus, so that would be plus 4/. So I can get rid of all this stuff. Plus 4/3 times what? 3 times 2 squared, that's 12. Minus 12 plus 5. Actually, I just I'll about to do that. And boom. As t grows without bound, these t's are in the denominator, meaning this entire thing here is going to go to 0 because the t's are growing without bound in the denominator. So my answer? Whoa. We can do it. It wasn't an easy process, but in the end, it actually was a Calc 1 integral, right? It was a straight up U-substitution. It was a Calc 1 integral with this extra twist of having an infinite limit. Okay, so there's two types of improper integrals. The ones where you have a limit of infinity and all you have to do is take the limit and just make that any variable you want other than x. And then it's just a regular old calculus problem and you take a limit at the end. We like this kind. There's one other kind. I'm going to give you the weekend to recover because that one is pure evil. That's the one where you're actually having undefined and vertical asymptotes in your integral. Yeah, this is the worst type. It's the other type of improper integral. And that's reserved to next day. Okay, so we are at a good place right now. Let me pause this.